Hi everyone, welcome to another episode of Conversations with an Astrophysicist. I am Scott Lewis, the creator of Know the Cosmos, also known as Scientific Scott down here on Twitter. With me, as always, is Dr. Katie Mack from the University of Melbourne. How are you doing, Katie?
I'm all right. How are you doing?
I'm doing well, thank you very much. And we also have a special guest with us to talk about our great topic. It's Emily Petroff. She is you're a PhD candidate at Swinburne University, also in Australia, correct?
Yep, that's right.
Fantastic. Well, thank you for joining us. It was actually last minute, and I really appreciate you jumping in on this not secret, but mysterious topic. Is that there was a signal found in 2007 from data in 2001, and we've been able to detect more of that in recent times, and also a lot of it's just from archival data. So it's these fast radio bursts. So that's what we're going to be talking about today on Conversations. Before we get started, though, I want to let you guys know how you can interact with us. We have the Q&A app installed, so if you're watching us either straight on YouTube or on Google+, you can open up the Q&A app, leave a question, and then if we're answering it on air, it will timestamp to when that's done. You can also contact us on Twitter. So as you see, I'm Scientific Scott. Katie is at AstroKatie, and Emily is at EB as in Bravo Petroff. And we will maybe respond to you live, but most likely we'll respond to you when we're off air. So, what are these? I mean, like I said, I might just go all Dalek and be like, explain? Like, what's going on here?
So first of all, Scott, I think you undersold this a little bit when you said like it was some signal. It's a really weird signal. Okay, so I'm gonna screen share for a minute and show you this thing. So
one time I undersell something. That's awesome.
Okay, so I don't know how easily you can see this, but this is a picture of the frequency versus time signal of the first one of these things detected. And what it is it's this tiny, really fast signal. So it was like 5 milliseconds or so, and just this blip, and it was really bright. So it was this radio blip that's very fast, very bright, and the frequency changed hugely over the course of however long it was going. So it was a few milliseconds, and nobody had any idea what this was or why a signal should look like this. And for like years, it was really unclear, like if this was really a thing. And this was called the Lorimer Burst. It was named after Lorimer, the person who found it. And they thought maybe it was some kind of weird, like terrestrial signal, or maybe it was some like blip in the instrument, or even some kind of alien signal. Like nobody had any idea. And
I mean,
remember
did they rule out pigeon poop? Because I know we have a history of thinking it might be pigeon poop.
I think it would have to be a really skillful pigeon.
Okay.
Like it'd have to be really fast.
Gotcha.
They're not
all right.
extended events. But yeah, so I remember going to talks about this after the first one was detected, but before any of the others were. And the big question was like, do these even exist? Like, was this just some kind of instrumental blip, or was it something else? So that's what we've been trying to figure out. And the like expert in this in Australia is Emily, who's here now, and I will let her explain more about like what we know about these things now, what else we've seen.
Yeah. Okay. So this one, just for some historical context, so this Lorimer Burst was the reason why it was so fantastic is it's so bright. I mean, we're used to finding pulsars that have this frequency time, dispersion delay, but those are normally in our own galaxy, and we're kind of used to seeing those with a particular amount of dispersion, and we didn't see that with this one. This one was above and beyond what we expect from the galaxy, so that hinted that it might be really far away.
So, sorry, can you explain for our audience what you mean by dispersion in this case?
Yeah. So
And you can explain this. That it looks cool, but also
Yeah.
looks like something I would see on my television in 1987.
Yeah. So
what,
if you look at the plot that Katie showed,
yep,
you'll see
right
you'll see
now.
that that there's a difference in when things arrive. So you see this kind of bright dark line that goes kind of across the plot, and that's showing that the signal is arriving at different frequencies at different times. And that's kind of like if you shine light through a prism, the blue light takes less time to go through the prism than the red light, because the medium in the prism is slowing down the light a little bit. And that slowing down is proportional to the wavelength. So that's the same thing here. We have the higher frequencies, which is the shorter wavelengths, arriving earlier than the lower frequencies. And that is called the delay, or the dispersion delay, because the process that's causing that is dispersion. And so we see this for all things that are traveling through the interstellar medium or the intergalactic medium, but we just had never seen something on this scale before. So
now, can I just jump in again for a second? So I think it's important to point out. So in this plot, you can see there's this long sort of stripe across the plot, and then inset is this little plot that shows a peak, and then just noise after
all
that.
Noise, right.
And the thing to keep in mind is that at any given frequency, this thing was extremely brief. It was only like a couple of milliseconds long, but it arrived at different times at different frequencies. So the higher frequency stuff, like if you had a radio telescope that was looking at just high frequency radio waves, you'd just see this really quick blip and it'd be gone. But then a few tenths of a second later, you'd see the same blip at a low frequency in a different telescope. So like the event itself was really fast. It was just stretched out by passing through space, and the same way that light is stretched out from a prism, it was stretched out as it was passing through space. But the initial event, whatever it was that created the light, happened really, really fast.
Mm. Yeah.
And so what would that, like, because I know, I think the biggest point going on right now is we have no idea what this is.
Yeah.
Have we ruled anything out? Do we know that it's not things?
Well, up until very recently, we had no idea. I mean, there were lots of different theories kind of circulating around. I mean, when the Lorimer Burst was first discovered, there's this big debate about whether or not it was even real.
Right.
And then starting in 2013, there have been a lot more discoveries as people have gone back and looked through old data and found that these things are actually scattered throughout all these old data sets that people just never thought to look for them. Mm-hmm. So we've actually built up a bigger population. So we have probably 9 of these bursts that we know about now. And we still don't really know where they're coming from. That's kind of the biggest question. We know that they're probably real because we have more than one of them now.
That helps.
Definitely. That was a big sigh of relief.
In science, it helps to research things that are real.
Absolutely.
And not made up, so that is good.
Yep.
Which it can also, and I think this is a good point to make, is that sometimes you do have to wonder, like, is this just a glitch in our detector? What's going on? And you could be putting a lot of resources into something that ends up having more noise compared to the signal and not being able to actually get something out of it. So I'm really glad that you guys have been able to go through the archival data, and you said all but 2 have come from the archival data. Is that right?
Yeah, that's right. So up until recently, we didn't have the technology or the capability to find these things in the data as it's coming from the telescope. So that was a huge leap forward when we got faster computers installed at the telescopes, where we can start looking for these things as we're observing. And in the past year, we've had 2 of these fast radio bursts happen while we were observing, and we detected them while we were observing.
Well, this goes to a question.
Let me just...
Yeah, chime in.
Can I just briefly...
Yeah.
So another important thing to mention is that another way that we know that these things are real, and also, on the sky, is that we've seen them in more than one telescope. So for a long time, there was only one telescope that ever saw these things, and that was the Parkes telescope in Australia. And there are reasons that it was the one that saw things. It was, the way that it's scanning the sky and the technology of the telescope.
But didn't Arecibo?
These things are hard to see. But then recently Arecibo saw one, so everybody was able to kind of breathe a sigh of relief and be like, okay, it's not just Parks like screwing with us.
Right. What's going on with you guys over in Parks?
Yeah. Yeah. Okay. Anyway, sorry.
We have a question here from the Q&A app from Carl Joseph, and he's asking, why is catching a live FRB such an important achievement? Does it matter when we catch it live as opposed to going through archival data, or is it more than just like woohoo, like we saw this live and now from more than one observatory? But is there anything fundamentally important for being able to observe it as it happens, as opposed to just going through old data?
Yeah, so this comes back to your question before of, are there any things that we've been able to rule out? And the best way that we can rule out where they're coming from, so we can say what they're not, is if we find one in real time and we try to look at it with other telescopes. And if we look at it with other telescopes, say like optical telescopes or X-ray telescopes, and we don't see anything, that immediately rules some things out about what it can't be. I mean, even better would be if we looked at the same spot and we saw something definitive. We could say, it's definitely that, and that would be super exciting. And the only way that we can do that is if we find these things as they're happening. A response a year later is not good enough. We really need to be quick, we need to catch them, we need to respond when we see one. So for the first time last year, we found one in real time, and we pointed all sorts of telescopes at it. So we got...
can I just jump in? When you say we, you mean you, right?
The royal we, Emily? Are we using the royal we here?
I mean, a team that I was leading, yes. Okay. So I let it in.
Just making sure you're taking credit for that.
Yeah, that's awesome.
Yeah, so last year I found one of these things in real time, and we got a team of 35 people around the world to point 12 telescopes at the same spot of the sky to look for anything related to this burst. And we weren't as quick as we could be. Like, we're hoping that in the future, when we find one of these things, we'll be able to respond within minutes or seconds. Seconds would be great, but minutes would be perfect.
Well, and that brings up a follow-up question that Carl asked as well. Like, how quickly would you need to get other telescopes pointing to the area when a new FRB is detected in order to find it useful? So what time would be ideal? Realistically ideal. How about that?
Yes, that's right. So I'd say unrealistically ideal would be great if we had all of these telescopes pointing at this patch of sky when the FRB happened. But to do that requires expensive telescopes to point at blank sky for an unknown amount of time.
Hey everyone, Parks is going unrealistic. Everyone point at what Parks is looking at.
Exactly.
Just in case.
So I think realistically what would be ideal is minutes. Is if we have the ability at Parks at least to find one of these bursts within 10 seconds. Okay. And so we're talking 10 seconds. We can tell other telescopes, and hopefully they could be on the sky within a minute or however fast they're able to respond. And that would be great.
So I have a question then from me. I know with Hubble we have a network of citizen amateur astronomers that are always looking up for certain signs that we know that could be having an event that could damage the Hubble Space Telescope. And so they work with our ops team in Baltimore that whenever this comes through, they know to shut it down. They're able to see these signs that something could be going on. Are there any signs, have you seen anything before these FRBs come in that be like, oh, we might be getting something from this direction, any sort of cues?
Yeah. The problem with that is these FRBs in radio appear to be happening a lot. So we're thinking that they're happening some of order of like 5,000 to 10,000 events over the whole sky every day. Wow. That's like an FRB every 10 seconds. And so you'd think that if they were observable with the techniques that we've been using up till now with other telescopes, that we would have seen them already.
Right.
So that kind of means we're kind of entering into this era where we need a new approach to how we do optical astronomy and X-ray astronomy to maybe catch these things simultaneously with Parks, because we don't see the kind of excesses in other wavelength data that we might be able to say, wow, there's a ton of this thing that we have no idea what it is, and then immediately say, oh, it's probably associated with these weird FRBs. But since we don't see that, that means that they're probably a little harder to catch than like.
So, I know both Katie and Ellen Duffy, Astro Duff from our other show, have written pieces on the FRBs. And have you written anything that's gone up besides? I know that the press release up on castro.org, which I will put. Actually, let me just screen share that because it is pretty, and I'll also share the image out because again, whoever was in charge of it did a great job of doing a graphic. Like, that is really cool. So this is the press release over at Castro, which is the Center of Excellence for All-Sky Astrophysics. And so this, this was really recent that this is going on. This is not, from this press release, this is pretty recent news.
Yeah, so we found this burst last year, but we didn't get the paper published until January of this year, so that's when all the press stuff started happening.
Okay. So what have you learned personally? Have you, has this given you a different insight into the work that you're already doing? Or is this what you were already focused on doing?
Well, we had never done something we'd never done follow-up on the scale that we did it for this project. So that already taught us something incredible. So we know a lot. We can put these constraints on where these bursts are coming from. So it's looking like they're not associated with supernova as we know them. They're not associated with these things called long gamma ray bursts. So that already gives us some answers, which is great. But personally, I learned a lot about, I think the biggest challenge in this project, it was extremely lucky and extremely awesome that we found one of these things. I think the biggest challenge for me was as a PhD student, managing a team of 35 professional astronomers, which was kind of intimidating, I'm not going to lie.
Pretty impressive. That's pretty impressive,
Yeah, you're pretty hardcore.
Not very many PhD students do that.
Kind of pestering everybody every day. Are you taking my observations yet? Are you taking my observations?
No, you should. Take charge of that. That's awesome.
Yeah, so that was the biggest learning curve for me, for sure. But yeah, I think our team learned a lot about how we're going to look for these things in the future, how we're going to respond, and the ideal way to get all these telescopes involved.
So can we talk a minute about what these things are? So so you mentioned a few things that we think they're not. Both Alan and I have written a little bit about what the possible models are, what these things might be caused by. Basically, you need something that goes boom very fast, right? You need something that produces a strong signal in radio, but doesn't produce a strong signal at other parts of the electromagnetic spectrum that extends for a long time. So it's not like a supernova where for 100 days you can see a bright counterpart in the sky. It's not like a pulsar where it continues. It doesn't seem to repeat. So what does that tell us about what these things are?
Yeah, so it is a tricky problem because, like we talked about that dispersion before, how much dispersion these things have. We think they're coming from billions of light years away. So you need something that produces a ton of energy on a very, very short time scale. So if you want to get all physicsy about it, you need an emission region.
Please, let's get physicsy about this.
You need an emission region that's tiny to produce such a powerful burst on such a short time scale, because you can't have something that's massive in space producing this very short burst. Physically, it just doesn't make sense. So you need this tiny, fairly small emission region. So we're talking hundreds of kilometers potentially. So something where something really extreme is happening. So we're talking about the most extreme physics to get this kind of bright burst from so far away. But like Katie said, it can't be optical or X-ray bright in the way that we're kind of used to dealing with. So I guess some of the theories that have been put forward for what could be causing these things are things like you might get a hypermassive flare, so some type of massive flare from a star called a magnetar. And these are energetic, really extreme objects that have very strong magnetic fields. And you might get a situation where the magnetic field of the star gets kind of tangled, and then all of a sudden it releases its energy, untangling the magnetic field, and this produces one of these bursts.
Right. So kind of like a solar flare from our sun, but like on a huge, much like brighter scale. So like our solar flares on the sun are produced by, reconnection of the magnetic fields on the sun, and they get these big prominences. But you need something with a much stronger magnetic field, and to do a really fast kind of flaring, bursting kind of thing. But I guess one of the issues with that hypothesis is that stars that flare tend to flare more than once, right? Like you don't just have one and it never comes back. And we haven't seen any FRBs in the same place twice so far, right?
That's true. Yeah, we don't know a lot about magnetar flares because we've only been studying them for as long as we've had radio telescopes and X-ray telescopes to study them. So some people have thought that these flares, an individual magnetar will only flare once in a while. So we're talking like kind of on time scales of thousands of years. So it could be that they do repeat, but that this repetition just happens on a time scale where we'll never see it. So that's kind of hard to rule in or out by what we've seen so far, which is tricky. But yeah, so I mean, we have been observing these things, and we've been re-observing them to see if they happen again. We haven't seen any repeat. So that already points to something that doesn't repeat on short time scales. So it could be either some type of flare that doesn't happen very often, or it could be something cataclysmic where you have an explosion or a collision that produces something very extreme.
Right. So I've seen thrown around ideas where it could be two white dwarfs that merge together and produce a massive explosion when that happens, or two neutron stars that merge together. My favorite model is the Blitzar model, which is you take a neutron star, and you have the neutron star pulling energy from pulling material from a companion or something, or maybe two neutron stars merging. Something happens where the neutron star gains a lot of mass, and it's spinning really quickly, and so it's got so much mass that it should collapse into a black hole because it's got more mass than a neutron star can handle. But it's spinning so fast that like the centrifugal force, in that sort of frame or whatever, like the rotation is keeping it from collapsing really fast, and so you have this like supermassive neutron star. And then it's losing energy, slowing down because it's like losing energy through magnetic fields or something. And then at some point it can't spin fast enough and it just collapses into a black hole and creates this massive explosion. And I just love the idea of, first of all, a supermassive neutron star, but then also we're seeing a black hole being created.
Yeah, I think it's pretty neat. I think it's
idea.
If it was true, I would love it. I mean, I can't say whether it is or not. I think it's just neat because you get this idea of like a neutron star that doesn't know it shouldn't be a neutron star.
Right. Yeah.
Figures out, it's like, oh, I'm way too massive to be a neutron star. It becomes, a neutron, a slightly larger than neutron star-sized black hole. And I mean, that would be physically insanely interesting because not only would we be getting all this information about cosmology and stuff, but we're also getting this very private information about black holes and how a black hole forms, and that's a really neat theory in my opinion.
Yeah, definitely. So I'm looking at the Hangout, and it looks like we might have lost Scott, and I don't know how that happened. But I think at the moment it might just be you and me. So one of the other things that we can use as a clue to figure out where these things are is the distribution on the sky, and this is something. Oh, he's back. Okay, good. This is something where we've talked about it. Scott and I talked about it before when we talked about gamma ray bursts. But just where these things are distributed on the sky can actually give you a clue as to like where they are in space, and that can then give you a clue as to what they could possibly be. And so we think that these things are outside our galaxy because there's this dispersion thing, where you get the signal gets more and more stretched out as it goes through more and more like intergalactic space. But there are also ideas where you could have like a really heavy, like a high plasma region really nearby, and it could go through that and get really dispersed. So so one of the things that makes us think that these are outside of our galaxy is where they are in the sky. So I think you have a picture of the distribution of these objects, Emily, or Scott? I don't know.
I do.
So,
I think I sent that around. Not sure how
I will see.
Okay.
What was the... Yeah, let me pull up that email. Sorry, my internet went down. So I'm back.
That's okay. We were fine. We did just fine.
I wholeheartedly believe in your efforts to do this without me. So I am just here to be funny. Let me pull this.
Yeah. So we've looked for these bursts all over the sky. We have all these surveys. We especially have a lot of surveys that are looking at the galaxy, because we study pulsars in the galaxy. We're very interested in the galaxy, so we have actually a lot of time that we've spent studying the galaxy. And we did that. We looked through all those surveys for these bursts, and we didn't find anything in the galactic plane. And if immediately that tells you, like, if you think that if something is from our galaxy, if it's a galactic population, you'd expect to see more when you look into the galaxy than when you look out of the galaxy. And that's not what we see. We see the exact opposite. So yes, that already tells us that they're coming from outside of our galaxy, not from inside. So.
Yeah, so let me... Scott, do you have that picture of the distribution of...
I've been trying to, and every time that I share it out, my browser crashes. So
right, okay, I see.
You might need to.
I'll share something. Okay, let me share this thing because I want to show you.
So what happens when you move people is if you move to another city, and all of a sudden everything, moving's awful enough as it is, but then you have to learn how to internet all over.
Okay.
There we go.
Okay, so I'm sharing, this is the distribution of gamma ray bursts in the sky. And this is one of the things that convinced us that gamma ray bursts were far away, which is that so this is a projection of the whole sky where the sort of central line is where the galaxy lies, and away from the central line, the horizontal line is outside the galaxy, looking out away from where the galaxy is. And since we're in a disk and we're looking through the disk of the galaxy, anything that's in the galaxy, there should be a lot more of it in the disk of the galaxy.
Uh-oh, did we lose Katie?
I'm wondering if this is a Google issue and not...
Yeah.
This might be a Google issue.
Uh-oh. Well, if people can still see it, I can say what Katie meant.
Are you back, Katie?
What? I'm here. Did you lose me?
Yeah, we did lose you. Which is, now we're thinking it's not just a Parkes Observatory or a Scott's computer thing, that this is more of a global thing and a universal issue.
Hold on a sec. Let me show you a distribution of stuff that is in the galaxy. So can you see that now?
Yes, we can.
Am I still here?
Yeah.
Okay, so this is the distribution of pulsars on the sky, and it's the same projection. So the central line is, and anywhere other than that, we're looking away from the plane of the galaxy. And you can see with pulsars that they're definitely more concentrated in the plane of the galaxy, because most pulsars are they're old stars that have collapsed and become neutron stars. They're inside the plane of the galaxy because that's where most of the stars are in the galaxy. And so you get this concentration right along the central line. But we don't see that with fast radio bursts. We see basically nothing on the central line where the galaxy is. So if they were in the galaxy, we'd be fantastically unlucky to have seen like 9 of them, and none of them are on that line. So it really can't. They really have to be really far away.
And that's what you're seeing from your data, Emily, is that it's not necessarily along along the plane, the galactic plane. They're all over the place.
Can you screen share that?
I don't actually know how to do it.
If it's along the left-hand side, there's a green button that says screen share.
Yes, I see it now. Okay. Sorry,
you can select the window that has the image.
Here we go. Okay, so is that working?
Yes, it is.
Yes.
Excellent.
Yes,
okay, so these are all of the FRBs that we found so far, minus one. There's one that's kind of like right here. That was the one that was found at Arecibo, and that's where the galaxy is the thinnest.
Right.
So we're looking, the center of the galaxy is here. This is sort of looking out of the galaxy along this line, and these are all the FRBs that we found at Parkes. And so we've looked extensively in this area around the plane of the galaxy and found nothing.
Right.
Yeah. So that's a pretty good indication that they're not coming from within our galaxy.
Which means it's not only coming from very far away, but very far as far as time goes. They're from a very long way back.
And also on the plot, you can see that these things are all discovered at Parkes because they're all in the southern part of the sky.
Yeah.
Yeah.
The direction Parkes is looking.
Parkes looks mainly sort of here, in this area. So it's much more. It's definitely a selection effect.
Right. They're not all just in that direction, but they're definitely not on the galactic plane.
Yes.
Yeah. Because another thing to realize about these kinds of observations is that since we have looked more at the galactic plane than anywhere else, we're even more likely to find them if they're actually there. So that's a selection effect that would make it more likely that we'd see a bunch of them on the galactic plane if they were there. So the fact that we haven't seen them, they're really very likely to be totally uncorrelated with how our galaxy is positioned, which means that they have to be really far away, basically. Which means they're really, really energetic things, and that's kind of awesome too. Right? So it's something fantastically cataclysmic going on somewhere out there.
Something beautifully disastrous, right? Something with that much energy means that something had, some major event had to have happened with those.
Right. Yeah.
We are running over a little bit on time. Also, we did have some tech hiccups. I'm a little okay with that. I do want to get to some questions here in the Q&A app before we go. This one here is by Keith Smith, and it's been upvoted quite a few times. Are the radio signals, quote, redshifted? Has the original radio frequency been deduced? So I think this would mean that we would have to kind of know the sources first so we can actually know that. But
we can sort of estimate how far away they're coming from based on that dispersion, so how much stuff they've had to travel through to get to us, because we can assume, we still don't know, but we can assume that there's an average amount of electrons per cubic megaparsec or something like that, per cubic light year, whatever, in the intergalactic medium. And then we say, okay, we see this much stuff, so it has to be this far away. So we estimate that they're coming from redshift, so redshift of about 1. So that means that, yes, the radio signal that we're seeing is slightly redshifted, so they actually were emitted at a slightly higher frequency, but it's still a radio frequency.
So a redshift of 1 means that the wavelength is about twice as long as it would be if it hadn't been redshifted, right? So if we're seeing something at I don't remember what the frequencies of these things were.
It's 1.4 gigahertz, which is like 20 centimeters.
Okay, so then it would have been originally 10 centimeters, but we see it at 20 centimeters because it's been redshifted, and that's because the universe expands. We talked about this before on this show, but as the universe is expanding, it stretches out the light and takes it to longer wavelengths or lower frequencies. And so in addition to the stuff that the signal is traveling through, spreading out the different frequencies of the original signal to different times, we're also taking the whole thing and spreading out, and we're taking the whole thing and shifting it to a longer wavelength, a lower frequency. Yes. And that's just because it's so far away.
So far away, right.
Yep.
Yeah.
Let's see here. We have some notes from our friend. So Paul Stewart, who's in New Zealand, says, "Tag Team Astrophysics is so awesome." Yes, I'm so glad that I've had both of you on. Thank you. I love working with Katie, and you've been fantastic, Emily. Thank you for joining us.
Thanks.
Although now Tiro Villa. One of the leading theories by various astrophysicists states that every time Scott Lewis relocates, a new gamma ray burst is emanated. It might just be the reflective, my albedo going on up here is what's going on. I know that we've had some going on with Twitter, just people commenting about being able to see this. So thank you all for tweeting and retweeting and sharing out. We've had actually pretty good viewership for it being sort of last minute on my end because I've been way crazy. Is there anything that you'd like to add about this, Emily, before we do our closing?
So talk about Superb.
Oh, yeah. So we currently have a survey going on at Parks. It's a new survey to look for these radio bursts called Superb. It's the survey for pulsars and extragalactic radio bursts.
Nice.
Yeah, so we had to get a good acronym because that's the rule in science these days.
Yeah.
Right.
Yeah.
You can't have a survey without a good acronym. So I'll quickly share our silly logo. Here you go. Superb. So we have.
That's awesome.
Nice.
I love it.
We have our little. This is a Superb fairy wren, which are native to Parks. So yeah, so the survey that we're doing right now is basically, it's an extension of the project that I was doing last year when we found one of these in real time. So from now on at Parks, any FRB that we find will be in real time, and we have this large collaboration built up to find them at other wavelengths. So
and, I mean, in this survey, like part of the survey is basically that you get to, like, if you see something, you get to like get tons of other telescopes where people are trying to do their own science and make them look at your stuff, right?
Yes.
Like you get veto power on everybody else's science.
Of a prearranged trigger is that if you actually find something, you can make everybody else
become lord of the telescopes. You're like, do my bidding. I have observed this.
Yeah, it's actually pretty neat. I mean, I was speaking with the kind of the people who are in charge of SWIFT, which is an X-ray telescope or gamma ray and X-ray telescope that's in space. I was speaking with them last year, and they were saying, well, we're really excited about these things. So if you find one, just wake us up in the middle of the night if you need to, because we'll point there. It's like, all right, that's exactly what I wanted.
Awesome.
Like people have they used to have beepers for gamma ray bursts where like if one went off, everybody on the team would get woken up whatever time it was, and they'd have to jump on their telescope and shift it. But I guess now there's probably an app or something, right?
Right.
Yeah, it's getting a little bit more sophisticated these days. So we're going for
Siri, move the telescope.
Yeah, we're hoping that some of this stuff in the future will even be automatic. So I guess the final message from here is just keep an eye out, because cool things are going to be coming out of Superb, and they're probably going to give us answers. We have a public website that I can send to you. I don't think I have it.
We can put it in the notes after the show.
Notes at the end too.
Yeah.
While we're gathering that up here, I was going to screen share, but I'm not going to screen share. But if you want to, you can take a look at planetary.org, which is the Planetary Society's website. Become a member if you'd like, because they're awesome. But Katie's blog is the case of the 5 millisecond cosmic radio burst, and it's a really, really good article, not just because Katie's a really good friend of mine. But then also, Alan Duffy had an article out on Cosmos Magazine, which is a great seg into a new thing Katie's been up to. So what's going on with you, Katie, in Cosmos?
Well, I now have a regular column in Cosmos Magazine. For those of you overseas, Cosmos Magazine is Australia's biggest science magazine for the public. It does all sorts of different science. A little bit sort of biased towards space, which is great. So this issue has a whole bunch of awesome pictures of planets and things, which is very cool. Anyway, so I have a new column in their viewpoints section, and and it's kind of funny because there are several people with columns in the viewpoint section, and their names like Lab Talk or Philosopher's Corner or whatever. And mine is just called Astro Katie. so
it's me.
Handle, which is weird, but anyway. So it's in there, and my first column is about dark matter, and it's I wanted to call my column "The Dark Matter of the Gaps," which is like a play on the God of the Gaps, which is this idea that like whenever we don't understand something, we get to like the edge of our understanding. There's some gap where we don't understand what it means. People say, "Oh, maybe that part's God," right? And this is like a thing that happens that people in sort of philosophy of science and religion and stuff talk about. Mm-hmm. So I wanted to call mine "The Dark Matter of the Gaps" because there's this phenomenon where a lot of times when we see some signal we don't understand in the sky, like excess gamma rays coming from somewhere, we say, oh, maybe it's dark matter, and then people come up with theories of how that signal could be explained by dark matter. And so I talk a little bit about that process and how that's kind of it's one of the ways that we need to look for dark matter, and it's a totally reasonable thing to do, but it means that a lot of times you get these newspaper articles saying, like, maybe dark matter has been found, and then it turns out to be some kind of jet from the galactic center of, from the black hole or something. It's not usually dark matter. So anyway, so check that out if you can in Cosmos Magazine. It will be on the web, I think, Monday night, Australia time, so I guess Tuesday sometime
I'm sure
in the US.
If you tweet it out, we might be able to.
I'll tweet it out, yeah, definitely.
We'll get you some coverage on that. And and you can also check out our previous episodes of Conversations with an Astrophysicist over at knowthecosmos.com, which we have had. We had a series. Oh man, how many episodes did we have about dark matter?
I think we had 3, maybe.
3, something like that. But and so we do like to take our time with any subject. So Emily, this also means that if you find anything new, please feel free to hit us up and tell us all the cool news coming forward. We would love.
Yeah, I think if something new happens, everybody will hear about it from me because I'll be over the moon.
Well,
okay, and you guys should all follow Emily. You guys should all follow Emily on Twitter.
Absolutely.
Because she shares awesome stuff there about these kinds of things.
And also follow Katie at AstroKatie and astrokatie.com. Yep. Your AstroKatie on Facebook and plus Katie Mack on Google.
Yes,
wow,
right.
I'm getting it down. My lower third is gone because my internet died, but I am Scientific Scott on Twitter, plus Scott Lewis on Google, and I believe Real Scott Lewis on Facebook. But you can find all of this and more at knowthecosmos.com, where we are teamed up with Castro, so down in Australia, but also with the Space Telescope Science Institute, which runs the Hubble Space Telescope. So until next time, everyone, I know we're way late, later than we normally are, but
there's just too much awesome science.
There's so much awesome, and you know what better way to usher in Valentine's Day, for at least for this part of the world. So this is some science love for you. You guys get 15 extra minutes of us. Okay, so you're welcome for them, and I'm sorry for me. So you're blessed with Katie and Emily, and you had to deal with me, so sorry about that. But until next time, we will see you all later. Thank you again for watching and for sharing this all up. And yeah, take care.
Bye.